All right, cool. All right. Hi, everyone. So my talk is called Hooking Nirvana, or Stealthy Instrumentation Techniques. And for those of you who've read the abstract, you're probably very confused about what on earth all those acronyms and names meant. So, brief little intro to myself. I'm Alex Ionescu. I'm currently Chief Architect at CrowdStrike. It's a security startup that you may have heard about. I've been over about 4 years working on the endpoint software that we build. And previously to that, and more relevant to my experience, I was doing reverse engineering of the Windows kernel, which I still am doing, have been doing since I was little, and worked on a project called ReactOS. And while working on ReactOS, I learned a lot about how the Windows kernel works, what makes it tick, and a lot of very interesting side effects and design decisions that were made on the way there. I then worked on the Windows internals books, which some of you may have read, and started doing training at conferences like REcon and others. And it's always a pleasure for me to talk about some of the little parts of the OS that are not very well known and that have interesting side effects, specifically when it comes to security. So this talk is going to be about five different types of those technologies. The first one is going to be time travel debugging, or Nirvana. We'll see what that is. Second one is going to be application verifier, or AVRF. Then minimalized windows, or MinWin. The application compatibility engine, or the shim infrastructure, or shim engine. And finally, control flow guard. Now we're going to see what the intended use of these things on a system was and is, and how their use can be misappropriated, misused, or leveraged. These are techniques that can be used both for defense as well as for offense. And we'll talk a little about how we can kind of detect and see that these things may be happening on your systems. So some of these techniques have been talked about before. So for example, the trick that I'm going to show you that uses Nirvana was discovered by someone called Nick Everdox, and he wrote an article on codeproject.com. What happened after that is Microsoft probably got annoyed that someone discovered this interface, and they completely changed it in Windows 10. So that article is no longer really relevant. MinWin had some good papers from Quark's lab and AR team, but again, they manually reverse engineered the structures, and their blogs were for Windows 8 and Windows 7. Windows 10 completely changes those structures, so again, that information is no longer really accurate for Windows 10. CFG has a really good white paper from Trend Micro, a really good presentation from MJ011 as well. They're really good papers on how CFG works, and we're not going to be looking at CFG in terms of an anti-exploit or mitigation tool. We're going to be looking at CFG as an instrumentation tool, and then those papers don't really cover that. And then AVRF, I haven't seen anyone talk about that except a really old blog post from a Russian hacker called TSS. There's not a lot of details there, but it touches a little bit on what I'll be showing you. And for the shim engine hooks, all I found is a Chinese article, which is actually pretty well written once you translate it. It's pretty well accurate for Windows 8. So some of this stuff has people kind of touching it on the side. Maybe some things have been looked at before. But kind of the point of all this is specifically take a look at how things have changed in Windows 10. So if you do read an article about Nirvana and you try to use it on a modern version of Windows, it won't work anymore. So here we'll see what some of those changes are, what data structures may have been modified, what version numbers you have to send now, new APIs, new mitigations that Microsoft may have added because they've seen people write blog articles about these things. And everything I'll talk about is on build 10,074. There are newer builds, but Microsoft refuses to release symbols for them. So without symbols, it's kind of hard to see what's there. I don't think they've changed that much between 1 month ago and today in terms of these types of things. But keep in mind that everything here is 10,074 and may yet change before final release of Windows 10. So we'll start with MinWin hooks, move on to Nirvana, then we'll do CFG, AVRF. Hopefully we'll have time for shims, and then I'll take any questions and wrap up. So first of all, MinWin. This is an actual screenshot of MinWin booting up, because you've never seen it before. And what is MinWin? Well, it's an internal Microsoft project to basically re-architect the layers of the Windows operating system. When David Cutler and his team built Windows NT, it was a very low-level micro kernel-based OS with a thin layer of drivers on top, subsystem, and then high-level functionality on top of that. And over time, Windows kind of grew into a beast. And then you started having dependencies over dependencies and circular dependencies and stuff that didn't really make a lot of sense anymore. And so around the Windows Vista timeframe, when this kind of bubbled up to the press and how successful Vista was, for Windows 7, they started kind of this internal project. And MinWin is never something that you'll buy or it'll ever ship in some sort of product name. But parts of it and parts of the architecture behind it are making its way in Windows. And so in Windows 7, some people started noticing some strange DLL names, either on their disk or in import tables. And those are tiny little DLLs that start with API-MS-Win. And these are basically part of what Microsoft calls API contracts for user mode applications. And in Windows 8, these contracts became kernel contracts as well. And the bootloader all the way down became aware of these API sets. Not a lot of people knew what this was for. And then in Windows 10, Microsoft announced one core, which basically makes you able to write a single application that works on all versions of Windows, including Windows for Internet of Things, Windows Server, Xbox, Windows Phone. And part of how they were able to do that was because of this relayering they had to do for almost half a decade, if not a whole decade itself. And the whole point of this was to create these API sets. And so, to quote Microsoft themselves, what API sets are strongly named API contracts. They provide a separation between the API contract and the associated DLL. In other words, if you're looking for create file, you don't need to know that create file is in kernel 32. You just need to have a DLL there that gives you kernel 32. And so the API, that gives you create file, sorry. And so what the API sets lets you do is allow the loader to perform a runtime redirection of the actual API set host DLL that implements the API that you want. And this lets you decouple the API names from the API providers and allows you to better factor the operating system, allows you to load less DLLs, because now, for example, if I have an OS where create file exists in a single 10 kilobyte DLL, that all it knows how to do is create files, I can load that DLL instead of having to load the whole kernel 32 DLL, which on Windows is 3 megabytes. And so the separation between contract and actual API implementation is what allows you, for example, to import an API that on Windows Phone may not even exist, but there's a stub implementation for it so that your application can still load. So how does this redirection work? In Windows 7, there's one single file, API set schema.dll. It's a PE file, and it contains a section inside of it called .api set. Kernel boots up and calls PSP initialize API set map, which verifies that this is a signed driver. So it is treated like a driver, and it has to be signed based on the rules of kernel mode code integrity. It looks up this section, maps it in memory, and finds the offset of where API set is. And then every single time a process launches, the API set is mapped in the process memory. So starting in Windows 7, you have this file mapped into any process that ever launches on Windows. The mapping is mapped read-only, but it's not mapped with a special flag called sec no change. And so what this means is that on Windows 7, you can actually make this mapping read-write and mess with it inside of your memory. And the address of this mapping is written in a special field called API set map in your PEB, which is a structure that every process has. So you can always find your map, and on Windows 7 you can modify your map as well, even though it's supposed to be kind of a system-wide map. The loader, which is ntdll, every single time you load a DLL, will then call a special function, ldrp apply file name redirection. It's going to go look in that mapping and see, okay, so you want API-ms-win-process-create.dll. You want the contract that lets you create processes. I'm going to go find out in your mapping what DLL implements that, which today might be kernel 32 or kernel base, and one day might be proc API.dll. Or on some machines, you're not allowed to create processes. So it might be a stub that just says you can't create processes. And all of that is done by the loader through this API set redirection file. And you can see why it's interesting, because this essentially means that anytime you now load a library, there's this PEB backdoor that actually takes you to the real DLL instead of giving you the DLL you thought you were getting from disk. Now in Windows 7, there are about 35 DLLs that are redirected this way. And they actually shipped a header file called API-set.h, which documented basically what that API set map looks like. So if you get the Windows 7 SDK, you have these two structures here, and basically the API set array is essentially this structure. That's what's in memory. There's a version, which was 2.0 in that OS, count, which is about 35, then you have an array of these structures down here. Each of these structures then gives you the name of the DLL and the data associated with it. So this basically is a conversion that goes from, let's say, api-ms-win-proc-create.dll, and it says on your system this is in kernel32.dll. Now, these API sets can actually have versions as well. So it's possible that in one day I might decide to have a create process extended function. Well, that one's going to be an api-ms-proc-create-2.dll, which means it's now the second version of this contract, and so the contracts can be versioned as well instead of just providing a redirection. So in Windows 8, you see a big change here. 365 DLLs are now redirected. And now you don't just have API set DLLs, which are used to separate contracts. You also have what are called extension sets. And extension sets are now used to basically check, here's an API that may or may not exist on your OS. I'm going to check if the API said it exists, and if so, I'm going to call it. So simple examples, every time you load a driver on Windows, we're going to check, is it signed? We always do that. But then we're going to check, is there a signing policy extension DLL? If there is, because you're on Windows Phone and Nokia installed one, that means that Nokia is also going to get a call, and Nokia is going to be able to say, I want this app to run because it's Nokia signed and I trust it. Nokia and Microsoft are the same company now, but let's say they weren't. On your desktop, you don't have that API set extension present, so the kernel is not going to make that call. So now, whenever you look at the Service Control Manager, kernel 32, the kernel itself, lots of other pieces of code, they now check, does this exist on your system? And if so, they'll call the extension that's there. Windows came with a kernel transaction manager, Windows 7, in Windows Vista. In Windows 8, it's optional. So on your desktops, you have tm.sys, and you have this API set here, extmswin-entos-tml1, which on a desktop system says tm.sys. On a phone system, there's no tm.sys, so that extension doesn't exist, and the kernel will never try making those calls. The other big change here is that this is no longer loaded by the kernel. It's loaded by the bootloader. So now as soon as you boot, and subject to the same policies as any other boot driver, the loader will load this API set. It can also load additional API sets. So you can actually have more than one schema. And all the schemas get merged together into a final API set schema, which then gets later passed on to the kernel. The kernel now maps it with sec-no-change. And so the addition of this flag in Windows 8 means that you can no longer modify your API set schemas, at least not through an easy fashion. And finally, the structures have changed as well in Windows 8. So now we're in version 4, and the structures look a little bit different. But they're still shipping the headers, so if you get the Windows 8.1 SDK, you'll be able to see the new structure and what it looks like. And basically, they added some flags, they added a size, they changed the structure a little bit, but they still documented it either accidentally or not, but it's freely available in the SDK. In Windows 10, the build that I have, 10,074, there are now 602 redirected DLLs. And now you can start seeing redirected DLLs for Xbox, for Windows Phone, for Windows for Internet of Things, for Windows Server, Windows Client. Now you really see how one core leverages this mechanism basically. And the API structures are now version 6 format. And version 6 is a breaking change. The structures actually change significantly. What used to be an array becomes an offset. These entries themselves now have a hash inside. So any tools that were written to parse the Windows 8 schema will no longer work on Windows 10. Basically need to redo the whole structures and write a new tool. The other thing that happens now is that when kernel base gets loaded, the delay load descriptors are parsed, and anything that starts with ext dash, if it points to kernel 32, we're going to load that. So there's basically additional logic in the code to support continued use of these min-win API sets. So if you wanted to parse them on Windows 10, it would look something like this. Now, don't worry, the slides are going to be available, so I don't expect those of you in the back to be squinting. But basically, it's fairly simple. You go to an offset, there's an array there, you iterate over the offset has other offsets, you iterate over those, and you eventually get a mapping of every DLL and its corresponding API set. So I wrote a little tool, and here's just a brief little sample of what that looks like. So for example, there's a DLL here, API ms win base boot config. Well, that's actually at VAPI32. Or if you're trying to get to API ms win composition dash window manager, well, that's actually UDWM. And if you're trying to get to win core atoms, that's actually kernel 32. And so the whole point here is you're no longer importing the DLL names, you're importing these contracts, and this file tells you where to find them. And it's not just user mode, it's kernel mode as well. So here's another example where there is a modern core dash win32k base NTGDI. And on modern core, that points to win32k full.sys. But there's also a MS-Win mobile core dash boot. And you can see that is an empty set. That's because on a desktop system, you don't have the mobile core libraries. You're not a mobile phone. So some of these things are going to be empty because they're simply not provided under your environment. Like, I have no idea what MRM is, but MRM Res Manager is present, but MRM environment is not present. And vice versa on a phone, things may look different. Some of these may be only on phone and not on desktop, and so on and so forth. Here's another example, this time the kernel. So kernel security, kernel signing policy are empty on desktop. But the file to do microcode updates, microcode, is actually pointing to entosx.sys, or isolated user mode, not present on the current builds. So let's say you want to modify this, because if you can modify this, that means you can now redirect execution towards other DLLs. So first of all, you have to decide what are you going to modify. Let's say you want to modify the heap APIs. Which of those contracts has the heap APIs? So Microsoft gives you a nice little website on MSDN where they document every single API that Windows has, including undocumented ones, and which API sets they're present in. So you identify the API you want to hook, you go to that web page, you see what API set it's in, and that gives you the API contract name. You can then iterate over the API set map, find that contract name, replace the string kernel32 with my kernel.dll, and now redirection will go to you. Now the thing you have to be careful with is that earlier in the tools output here, you saw that, for example, fibers and file were all pointing to kernel base. That string is actually aliased. And so anything that's basically saying kernel base is going to have the same offset to kernel base. So if I replace this with my base, then everything else is going to become my base. So instead of basically overriding the pointer, what you have to do, if we go back and look at the structures, is there's an offset field. So you change the offset to another offset, and then your entry has a different offset than all the other entries. Now that means you have to allocate a little bit more space in that structure. You basically allocate your own buffer, and you point that offset to that new buffer. There's a few gotchas or caveats when you try to do that. The first one, as I mentioned, is that API set map is mapped as read-only. And in Windows 8 and higher, you cannot remap it as read-write because of that special seg no change flag. So a much easier modification to make is edit the PEB, because the PEB points to the API set map. So you read the existing map, allocate an identical one plus a page, copy the old copy on top of the new copy, make the changes that you want to make, and then overwrite API set map to point to your copy, because the PEB is writable. And so that pointer can be changed to memory that you control. The other thing to be careful about is that the redirected DLL name, if you notice there was no full path in those screenshots, right? It just said kernel base. And that's because the assumption is that all the target DLLs are in C Windows System 32. Now, C Windows System 32 is an admin directory. And so if you're trying to redirect or hijack an application and you don't want to have to be admin, that kind of stops you from dropping DLLs in there. But you can just name your DLL /spool/driver/caller. You may be wondering, why on earth would you name it this way? Well, because this is an actual subdirectory under System32. And if you go to C Windows System32 spool drivers caller, it's a read-write directory for users. So you can drop your DLL in there, and then the name of the DLL will actually be the directory of the DLL, and then it'll load the DLL there, even if you're not admin. The last thing to worry about is that if you yourself are then hooking an API that's in kernel 32 or kernel base, or an API dash whatever, when you actually try to call the real API, your own lookup of that API will itself be redirected back into yourself. And so what you need to do is build your own import library where you import directly from the host, where you know exactly that heap.alloc is in heap.dll, and you import from heap.dll. Otherwise, if you use the normal Windows libraries, you'll import from yourself, and then you'll just spend forever and ever and ever. So I'm going to show you a demo of basically how to implement that with a simple library that basically hooks all of the heap APIs, build that library, and load Notepad with that change, and hope that it works. So this Notepad's going to go up to here. Come on this out. So just to show over down here, we basically have all the hooks for heap alloc, for heap free, and heap alloc and heap free, for example, they're doing a debug print, and then they're calling the original function. And then there's hooks for all the other heap APIs that have to exist. So heap query information, heap set information, heap validate hook, heap create, etc. And then basically a simple definition file that says, you know, here's all the original APIs, and here's my hooks for those APIs. Just because if I call them the same way, then I can't. I could call them the same way, but then I'd have to dynamically import the other ones as well. So if I build this library, it's going to go in C Windows System32 spool/driver/caller/test.dll, and users can write here, and I'm not running the compiler as admin, so you can see I was able to write it in there. And then I have a simple loader that's basically going to load Notepad, standard create process call. And we're going to go look for API-min-core-heap-l-2-0. That's the contract for the heap API. And we're going to be parsing the API map of Notepad. And we're going to be looking for that contract. And when we find it, we're going to override it with spool/driver/caller/test.dll. So basically, we're saying that this is the name of the DLL, which matches the location in System32. So I'll put a breakpoint on the resume. Okay, and then I can open up a debugger and try to see what will happen. Hit go. So you notice there's a module load, caller test.dll. And I've hit go, and I'm going to resume it on my end here. And there's Notepad. And there's the debugger. And for example, you get to learn that every time you type a character, there's 2 allocations and 1 free. And every time you backspace, 2 allocations and 1 free. And if you just backspace and there's nothing, just one alloc and one free. So clearly, that dump there, I know you may not be able to see it, but it's basically those are our debug prints confirming that basically every single heap alloc and heap free is now gone to us. And we haven't had to, we haven't done any of the traditional hooking things here. All we've done is change the structure of memory. That's the API set map. And so if you're an AV company and you're looking for hooks, right, heap alloc and heap free are not hooked. There's no inline code hook there. The IAT hasn't been patched by someone malicious. This is just using the exact same min-win functionality that's already there in the system. So how do you differentiate this from something legitimate from something illegitimate? Well, one clear sign here is that DLL name, right? Spool / print / caller, probably not where Microsoft is going to put their DLLs. So that's obviously a telltale sign that something's off there. But if I did have admin rights, I could write it in system32, right? And I could have called this heap API.dll, and you wouldn't necessarily know that it's not supposed to be there. But not just on the defensive side, this is actually a pretty cool thing you can do, because now I have a heap instrumentation library, and I can instrument all heap APIs, and I didn't need to do any kind of weird detours or patching or playing with known DLLs or any of the weird things that you normally have to do. So that's an example of one of these, what I call dynamic instrumentation techniques. Thank you. Thank you. Now, while doing this research on this specific one, turns out the API set schema doesn't have to be signed by Microsoft. It has to be signed, but not by Microsoft. And it turns out there's a registry key that lets you put additional custom API set schemas on disk. And there's some parts of the kernel that, for example, check, is this API set present? And if so, I'm going to make all my system calls go through it. Or this API set is present, I'm going to make all my process creation go through it. So if you create the right API set with the right API name, and you have to sign it, but it doesn't have to be signed by Microsoft, and it's easy to get a non-Microsoft signature these days, you can basically hook every single kernel API that PagerDuty would normally mess with you. And you get a nice little sexy persistence mechanism where all you have is a DLL on disk, which is a fake additional schema, a registry key to point to that schema, which none of the AV companies know to look for, and you're basically golden. Well, it turns out that while working on these slides, my PowerPoint crashed. Microsoft security got the dump, and just by random chance, PagerDuty in Windows 10 now protects against this exact trick. So in Windows 10, if you try to change the API set map in kernel mode, PagerDuty will actually crash you. So you can still do what I just did in Windows 10, no problem in user mode, but in kernel mode, if you try to mess with drivers this way, they'll figure you out. So it's nice to see Escape and Skywing being ahead and figuring these things out. All right, so next thing we're going to look at is Nirvana hooks. And what I try to do for every single section is I went on Google image search, and I picked the first image that I could find for each of the things I was going to talk about. So for Minwin, it was that bootloader screen. For Nirvana, that's what came up. I didn't feel like searching more. So what is Nirvana? Again, in Microsoft's own words, Nirvana is a lightweight dynamic translation framework that can be used to monitor and control the user mode execution of a running process without needing to recompile or rebuild any code in that process. This is referred to as program shepherding, sandboxing, emulation or virtualization, dynamic translation, blah, 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 blah. So it's basically Microsoft's internal translation, dynamic translation framework. Now, using this framework, they've built tools like iDNA, time travel tracing, TrueScan. And if you've been at conferences or read Microsoft research papers, you're probably seeing these amazing, incredible technologies being referenced time after time after time again, and never ever got the chance to use them because Microsoft does not ship them publicly. But how does Nirvana, the internal tool that they have, do its job without angering PatchGuard? If you want to dynamic instrumentation across the entire OS, you need to hook and patch things in the kernel as well. And if you do that, PatchGuard is going to crash your machine. And so in Windows 7 SDK, it turns out there's a dynamic instrumentation callback that got leaked out on the SDK. And basically, they showed you that by calling NTSetInformationProcess, you passed in the process instrumentation callback class, and it takes a pointer to a function. Once it takes a pointer to that function, any single time that the kernel exits the user mode because of a system call, because of an exception, because of an APC, because of NT-continue or call or user mode callback, or because of process startup or thread startup, basically any single point through which the kernel ever returns into user mode, that callback gets called first. And so you get to basically hook and intercept every system call return, every APC, every callback, anything you could ever want to, which makes sense if you're a team building something like Nirvana. You're going to need the OS to provide something like that for you. And so in Windows 7, you basically have a one-liner NT set information process. You pass in process instrumentation callback as the type, and you pass in your callback, and now it calls your function anytime one of those things happens. Now, this only works on x64 Windows. It doesn't work so well on 32-bit applications, and you need to have debugging turned on. And it doesn't catch everything. And you need a privilege as well. So it wasn't super useful because of these limitations. In Windows 10, however, you now register this in a different way. You have to pass in a structure. The structure has a version, a reserved, and a callback. So you still put your callback here, but reserved has to be 0, and I always love it when someone adds a field that always has to be 0. It's like, let's just add more data. And the version depends now if you're running on x86 or x64. On x64, you pass 0, but on x86, you pass 1. And yes, now on x86, this callback is supported. And it also supports WoW64 application, and it doesn't need the R7 to be set anymore, so you don't have to be actively debugging the application, and it also now catches NT-continue, although apparently only on x86. And so in Windows 10, this now becomes a much more kind of widespread thing you can do, because it'll get all applications, x86 apps, x64 apps, x86 app is running on x64, and you don't need to have a debugger attached to basically instrument what the kernel is doing. Now, in order to support x86, they also added a few changes. So for example, as you know, on x86, stack control is a little bit harder than x64, because among other things, parameters get pushed on the stack. And so in the tab, you'll notice 3 more fields: instrumentation callback SP, previous PC, and previous SP, which basically gives you the stack, the previous stack, and the previous instruction pointer. Because if you're the function that gets called now, instead of what the user expects to have been called, you have to know how to eventually get back to what the user expects. And if we're not running with you corrupting a stack, you have to know how to bring the stack back to where it was. And you also run the risk that your instrumentation callback may itself make an API that then calls back into your instrumentation callback, which then calls back into your instrumentation callback. And so in the tab, you can flip a field that says instrumentation disabled, and while that field is true, then you can not recurse into yourself. On x64, you don't really need those fields, because parameters are passed through RCX, RDX, R8, R9. It's not going to touch the stack. You don't have to worry about a 16-bit stack or 32-bit stack. And so instead, all you have on x64 is R10 contains the previous instruction pointer. So your callback routine gets called with R10 containing the previous instruction pointer, and then when you're done instrumenting, you just jump back into R10, and everything resumes back to where it's supposed to. So if you wanted to write such a callback, obviously it would have to be in assembly code, or at least it would have to begin being in assembly mode, because to read R10, you need assembly code. And you also have to realize the fact that at this point, the kernel has returned back to user mode, restoring all of the non-volatile registers to what they were. And so now if you do things to the non-volatile registers without preserving them, you're going to crash the user mode application that's expecting the call. On top of that, you have to worry about whether or not this is a system call. Because if this is a system call, what has the kernel also returned? The return value in RAX. And so if you now use RAX, you're going to destroy the original result value that should be returned back to the user. And so you have to obviously write a bit of intelligent code to determine if this is a system call, if this is an exception, what to preserve and what not to preserve, and not just write some assembly code and hope you get it right, which is what I did. So let's look at a little demo of how that would look like, and then hope that one works. So basically, I'm actually gonna use the same technique to basically load that same DLL, the heap API hook DLL. So actually, I'm gonna change techniques, but this time the heap API hook, instead of debug printing heap APIs, I'm gonna make it call a dummy function. And that dummy function is going to be in another DLL. And what this DLL is going to do, it's going to open up a console. So when Notepad boots up, you're going to see, hopefully you're going to see a console prompt. And then I'm actually going to initialize the debugger engine. And we'll see why I do that. And then I'm setting up the Nirvana hook here. And the Nirvana hook points to instrumentation hook, which is a little bit of assembly code. So I'm going to set up the assembly code right here. And this is a really dirty hook that's barely going to work at all. Notepad will not be able to initialize with what I've written here. This will basically just get us far enough into a piece of C code. And then in that piece of C code, where is it? There we go. In that piece of C code, I'm basically calling sim from adder, and I'm going to print out on the screen basically the symbolic names. I'm going to use a symbol engine to print out what are the targets of that API, if it works. So let's see. Everything here looks good. Let me just disable the. Okay. So build the instrumentation library. Yeah, there we go. Build. Okay, that worked. And disable the CFG hook, which I'll show you later. So let's get rid of this code. Okay, that's good. So I've got the instrumentation hook. Now this one I'm going to copy to system32 because I was lazy and I gave it a relative name. So instrument.dll system32. So same thing, I'm going to start Notepad with a little loader, and this time that dummy function should be called, and we should see some things. So again, I'll attach to the debugger to see what that looks like. I'll kill the old windbag, we don't need this one anymore. No, I should not be seeing those heap APIs. So I think my DLL was still in use. Stop debugging. I'll do a rebuild. Rebuild test.dll. Okay, try it one more time, otherwise we'll move on. File. There we go. So this font is tiny. Let me make it less tiny. So basically, this is the console that Notepad is now bringing up because our DLL is injected. And the instrumentation hook is revealing every one of the calls that got made. And by using the symbol engine, I'm able to see basically what system calls are being made. And since we're hooking the return here, we're not hooking the system call, we're hooking the return. We're seeing, for example, that whatever key was queried here, EX returned object not found. And this is without, again, any inline hooks or any system call hooks. We are getting the return, not the call, but there are other ways to hook the call. And this, again, can be extremely useful in terms of hooking and also understanding what's basically going on with the system. Now, because of the way I've written it, if I hit go here, it'll eventually crash. You can see it. I actually hit a crash here because of the stack exhaustion, and that's just because I didn't have time to polish this up. So eventually it dies, and if I hit go, it'll just die there. But having done this better, it could have kept on going and going and going, and we would have seen all the user mode callbacks that are done by the graphics engine as well. And of course, then you can start doing things like figuring out based on what these APIs are, what the parameters were, and I could basically decode every single parameter and all the functions and so on and so forth. But the point is just to show you, here's another tool that lets you do that and not rebuild pin for you. So that's that. So the next thing which I'll talk about is CFG hooks. and when searching for a control flow guard hook, this was the first thing that came on Google Images search this time, which I guess is for water flow. So what is CFG? CFG is basically a new mitigation that Microsoft has added in Windows 10. And again, their explanation is what CFG does is when you compile and link your code, it analyzes and discovers every location that any indirect call instruction can reach. It builds that knowledge into the binaries in extra data structures, and it injects a check before every indirect call in your code that ensures the target is one of these expected safe locations. If that check fails at runtime, the OS closes the program. So some check is being injected here. And basically, when you compile a binary with CFG, an indirect call, where basically you have, let's say, a database object and a hash function. Now the hash function gets copied into temporary. There's a guard check I call f pointer, and then if that hasn't exploded, then we call your function. And guard check I call f pointer is normally, when you build the library, a pointer to another function except validate jump buffer. And except validate jump buffer is just a ret. And so this means if you just run this binary on a non-CFG aware operating system, you'll just basically take an extra call ret, call ret, call ret, call ret, call ret before every single runtime function. So the loader must therefore be doing something to make this more useful than just a call ret, call ret, call ret. And so when you build a PE file, you have what's called the image load configuration directory. And this was used back in the NT4 days for app compat hacks, for setting limits on your heap, for debugging, and a bunch of other old deprecated things. And more recently, when they started adding security mitigations, this structure became more interesting. So for example, the pointer to your security cookie, so that a loader can update it, is an image load config directory. The trusted SEH routines are in the load config directory. And in Windows 10 and 8.1 update, when they introduced CFG, they added 4 more fields: guard CF check function pointer, guard CF function table, guard CF function count, and guard flags. And in Windows 10, there's a few more interesting things in there that you may want to look at. So that guard CF check function pointer is basically something that LDRP config load config, process load config is going to read. It's going to take that pointer, which is a pointer to that NTDLL guard function, make it read write, and then override it with LDRP validate user call target. And it does this if your image is linked with CFG and if you've enabled CF instrumentation with CFG. So basically it does this only for binaries that are CFG aware. And so what used to be here, statically accept validate jump buffer, becomes LDRP validate call target. And what the load config directory has is a pointer to this. And so the kernel, the loader, overrides this with that, and so this function gets overridden, and now that function is the one that gets called all the time. And then it verifies, basically, what CFG does is verify using a bitmap, is this call allowed or not. But again, I'm not going to talk about kind of the implementation of CSG. Others have done that already. We're interested in, well, hold on, if there's a CF guard checking function, why can't I put my own function in there? And so we can basically replicate the exact same thing that the loader does, and in our image load config directory, or in the image load config directory of another application, overwrite that stub function with our own function. And then again, we have to write some assembly code, because we're going to be basically right before the real call happens. And again, we have to be careful about preserving non-volatile registers and what registers we mess up with. And again, we have to write some assembly code, which can then call some C code. Now, in that C code, or that assembly code, you'll then be able to intercept every single indirect call that any application or that the application you've hooked makes. So we now have a way to intercept all indirect calls. We have a way to intercept all API calls, and we just saw a way to intercept all kernel to user calls as well. And so a guard CF function is basically very simple. You get the call that's about to be made in RCX, or on x86 it gets pushed on your stack. You will validate that, or you can print it out instead, and then you can see what all the indirect calls that the binary made were. So basically, we can go back to the victim process here. and re-enable some assembly code which contains a CFG hook. And it's an example of how one would implement this. We're basically getting the load config directory, just like the loader would. We're making it read-write, just like the loader does. And then we're overriding the guard CF check function pointer with our own pointer. And having done this, we then restore it back to read-write, to whatever it was, to the old one. So now CFG hook is going to be called every single time there's an indirect call. And what the CFG hook does is pretty much the same thing that the other hook was doing. Call sim from adder and try to see the symbolic address. But this is not going to be as useful because most of the time indirect calls are not actually just symbolic addresses, except when you're calling like NTDL function pointers. Most of these indirect calls are going to be internal Notepad function calls, internal Notepad C++ tables, or internal IE tables. So it may not necessarily have the symbols for all of those. But we should still see some printfs for pretty much all the indirect calls. So I'll do that, and then I'll disable the instrumentation callback so that we don't have both of those kind of fighting for runtime. Okay, so the debugger's dead. Recompile. Recompile test. Recompile instrument. And then copy instrument into system32. So again, I'm going to load Notepad, and now this DLL, which is being injected through minwin. So we're still using minwin to inject the DLL, and then that injected DLL is overriding the CFG pointer of Notepad, and we should start seeing some indirect calls. So attach to Notepad. Hit go. Okay, and then resume Notepad. Beautiful black screen. Yep, not so good. Okay, let's see if I can quickly figure out what I forgot to do. There's the CFG C hook. CFG hook is calling it, and DLL main is doing that. Dummy is doing that. Well, I'll try one last time. If not, for the interest of time, I'll move on and put a breakpoint and see maybe what went wrong there. Oh, nothing went wrong. I had a breakpoint on like an idiot. Well, the breakpoint should show that, yes, indeed, it did work until I killed it. So yeah, now it's... I'll just redo this. So it was obviously working. Stop debugging. Run. Attach. Cleared any breakpoints I may have had. Hit go. Hit go again. And there we go. So these are the CFG hook detection. So this is basically, these are all indirect calls that Notepad has been making, including, it would appear, an indirect call to ZW query system information. The compiler is actually smart enough to add these checks when you're doing get proc address as well. So among other things that a CFG hook will see is anytime someone does a get proc address, and then any other vtable callback or anything like that. So those are CFG hooks. Now, while I was kind of looking at this, I was just doing a lot of reversing, and just wanted to point out there's a lot of stuff in CFG that people haven't really talked about yet. For example, the Nirvana hook that I just mentioned, I thought about, hey, couldn't you make a bypass where basically, since Nirvana hooks are called by the kernel, you could bypass CFG since the kernel wouldn't know to verify the CFG bitmap. It actually does. So if you try to set up a Nirvana hook to something that CFG doesn't know about, it won't let you do that. You may also know that no execute protection has ATL thunk emulation, which emulates certain instructions that look like ATL thunks, Well, they actually make sure that when they're emulating those thunks, they're not calling into a fake thunk that could bypass CFG. So there's actually some CFG bypasses, which I didn't see anyone talk about, but it looks like Microsoft has basically mitigated against them. There's also an RTL guard is valid stack pointer. And when you turn on CFG, it turns on some stack checks as well. So if you try to do like an NT continue or set thread context, you try to raise an exception with a stack that's not in the valid range, even though that's not really related to control flow, by turning control flow guard on, it now mitigates against those types of attacks as well. And in Windows 10, there's a new set protected policy and query protected policy. And according to MSDN, this lets you set up GUIDs with data in a special protected heap that if you have control flow guard turned on, no one can touch or modify after the protected data has been put in there. So it looks like CFG actually covers a number of other technologies, not just calling in direct functions. And it would be great if more research was put into that. I didn't have time for it, but it looks like there's definitely a lot more to it than what people have been assuming. So the next thing to talk about is AVRF, or Application Verifier. An Application Verifier is basically a tool released by Microsoft. And what it does is dynamically identify bugs in applications. So basically, they subject the application to stress, they subject the application to API hooks, and using those hooks, they verify if the application is behaving properly. So it finds subtle programming errors that might be difficult to detect. So how do they do that with Application Verifier? Well, when you have Application Verifier turned on, and we're going to see how that can happen, there's a special DLL called verifier.dll, which the loader knows how to load with a special function called avrf mini load DLL. That gets a special RTL verifier helper table, and then you can interact with application verifier providers. That helper table contains an RTL verifier heap table, which lets you override every single heap API. And the reason they implemented this was for what's called a page heap, which is basically a debugging technique to see if you have overridden a single pointer in the heap due to an off by one. With this, you're actually able to have a whole page of heap, and you do an off by one, and it'll crash the machine. But basically, if you call yourself verifier.dll, then you can hook all the heap APIs. But that's not super interesting, because calling yourself another DLL name, we all know how to do that. But how do we turn it on? And what happens when you turn it on? So for verifier.dll to be loaded, you have to have one of these two flags that are called global flags, FLG application verifier or FLG heap page allocs. When those flags are turned on, then verifier will load. And how are they turned on? You have to write global flag and set it to 100, which is basically the equivalent of FLG application verifier, and or FLG heap page allocs. At that point, verifier will be turned on. But then there's another field in there called verifier DLLs. And anything you put in there will be loaded as an application verifier provider. And there's actually a malware out there called Trustfire that uses that. So what do providers do? Well, providers are loaded based on that verifier DLLs key or on another key called application verifier global settings. And for example, if you have a provider that's called vrfcore.dll, and it doesn't matter on what directory it is, so this is just checking the name, not the full path, and you have a function inside of it called avrf API lookup callback, then every single get proc address that anyone does goes to you first. And you get the caller of who did that get proc address, and you can change the result of the get proc address. So that's pretty neat. But not just that, verifier providers can hook any single exported function of any DLL they please and have the system do the hooking for you, and have the system deduplicate multiple hooks. So that there's multiple hooks to the same function. The verifier package will basically build a chain of hooking functions without you having to worry about that. And if you set avrf debug to true, you can basically see app verifier doing all of this stuff. So how can you write a verifier provider so we can be loaded? So you basically write a DLL, and when you write a Windows DLL, I'm sure you've heard about these 4 different reasons: process attached, process detached, thread detached. Well, there's a 4th one called process verifier, which I'm sure you probably did not hear about. And when you get that one, you have a special structure called the verifier provider description. And in that structure, you put a number of thunks and a number of API names and a number of function names, and it hooks them all for you and points to your code instead. So I won't bore you with the structures, but that's what they look like. You'll see them on the slide. And this is a very simple hook, for example, for close handle. If I want to hook close handle, I put an AVRF descriptor that says, here are my hook DLLs, and my hook DLL is kernel 32, and my kernel 32 has some thunks that I want to hook, and the thunk that I want to hook is close handle, and close handle is close handle hook. And close handle hook is my little function over here, which then calls thunks.thunk old address, which got automatically put in for me, and then I can debug print the result. So I basically have an automatic hooking and injection mechanism through app verifier where I didn't implement any code at all except these 8 lines of code, and the system did everything for me. And it looks like it's done by something legitimate. The other thing that's crazy about app verifier is that it actually gets loaded before kernel 32. So obviously here I'm importing from kernel 32, so I'm forcing that to happen. But my DLL in it will run before anyone else's DLL in it. So you actually get execution before anyone else has gotten a chance to run yet. So last little demo will be the verifier demo. So I'll stop this, close the debugger, and I'm going to go in regedit, turn on verifier, and I've got a DLL called verif.dll, and now when I launch Notepad, verif.dll should load. So now I don't need a special launcher. Open executable, notepad.exe. So you notice a bunch of debug prints, all of those from the verifier engine because I've turned them on. And here's Notepad and NTDLL and then verifier.dll. And after verifier.dll got loaded, it says an initialize the provider verif.dll. And here it is, before kernel 32, before kernel base, before anything else, my DLL got to load. My DLL then said hello, hacky verifier on. And at this point, I'll let Notepad run. And every single time Notepad closes a handle, there's my debug print, because I'm hooking close handle. So that is the app verifier hooking. Thank you. So one thing to note is that to turn this on, I had to go in the image file execution options in registry key. And that registry key is system access only. Well, it turns out that there's a flag in shared user data called image file execution options. And if this flag is set to true, then it's going to read the image file execution options from a per user hive. In other words, allowing any unprivileged user to turn on verifier like I just did for an admin app. And then when an admin app loads, it'll load your DLL on your behalf. Now that is disabled by default. But if you do turn it on, or if someone turns it on your machine with this very little known flag that's actually documented on an obscure MSDN page, then you're extremely vulnerable to anyone basically turning on verifier without even being admin. Because at least now you have to be admin. So it's mostly an instrumentation technique, not a malicious technique, because if someone's admin, they can do other things as well. But you may want to make sure that that flag isn't kind of set to true. And the last thing I'll quickly go over while I have my 2 minutes remaining is shim hooks. So the shim engine, as I'm sure you know, is the app compat engine, which allows Microsoft to basically install shims that are essentially, again, API hijacks that allow you to redirect execution. And basically, this shim engine is loaded by a function called ldrp init shim engine. And this one gets called whenever the PEB's shim data has something inside of it. This then calls ldrp get shim engine interface, which gets a bunch of function pointers. It then calls your entry point. And then for every other shim plugin, it calls some functions inside of you. And there's essentially a whole list of APIs that if you export them with this name, you're going to be called at process startup. You're going to be called before initialization, after initialization, when a shim gets loaded, when a DLL gets loaded, any of these things that happen, including whenever someone calls get proc address, just like with app verifier, you get a callback. So how do you get that to activate? Well, all you have to do is make sure that pshim data is not set to null when you create a process. And what should you set pshim data to? A Unicode string to a DLL name. So basically create a process, suspend it, set pshim data to c/foobar/evil.dll. Now evil.dll gets loaded as a shim engine, and as long as you provide the correct exports, your shim engine will be called, and now you can monitor all of those things, including all DLL name resolutions, including all get proc addresses. And this is yet another way of instrumenting and hooking pretty much everything that a process is doing. You can also install this dynamically. This is the only one that can be installed dynamically. Every single thing we saw had to be done at startup, either through the registry or with your own loader. This one, if you call LDR init shim engine dynamic on something that's not already shimmed, you can then basically hook it with everything we saw on the previous slide. So this one doesn't require you being there at startup in Windows 8 or later. And then you can load any other DLLs that you want that way. So in conclusion, Microsoft has built in a number of shimming, hooking, wrapping, verification techniques in the kernel and in user mode. Most of those are undocumented. They require structures that are not well known, that have changed. They require APIs that are kind of secretive. And all of these not only allow you to hijack an application and instrument it, but in some cases also have persistence, and in some cases defeat emulators as well, right? If someone's trying to understand your control flow and you're using all these OS-provided ways to jump from one place to another or to hook things, it's a lot harder for someone to understand what's going on. And you can imagine someone using App Verifier and the shim engine and a Nirvana hook and a CFG hook and using everything we've talked about today and basically have complete control of a process without having a single inline code hook or any of the traditional things you would try to do when you're monitoring a process. And the last piece of knowledge I'll leave you is please take a closer look at CFG. There's a lot of stuff there people haven't talked about. So that's it. Thank you for listening. Questions? Cool. I've got time for questions. Sergey?
So there are those 4 hooking engines, right?
5.
5.
Yeah.
Between them, do they cover the functionality of dtrace?
The one thing that you won't be able to see, which I think dtrace covers, is CPU register modifications, like control registers. I think dtrace catches that as well. But other than that, because you can hook any API, any indirect call, and any return from any system call, you can basically hook anything at all, assuming the binaries have CFG enabled. If they're not compiled with CFG, for example, then you won't get indirect calls.
So do you see all of those engines converging into one eventually, or is it?
No, it's Microsoft. They like to make sure they do 8 things of the same thing. So there'll probably be more engines as time goes on in time.
So that was my thinking while I was,
Yeah, it happens a lot. Not invented here.
All right, thank you.
Thanks.
Hi. I have a question about the API set map.
Mm-hmm.
Because you have said that we can hook the API set and redirect each API inside the new DLL that you write. But I have not understood 2 things. The first one is that the notepad.exe import directly from the APSet map DLL and not directly from, for example, for a standard DLL. Is this kind of hooks useful only for those applications or for the all application that import even standard DLLs?
It's actually useful for both. So what's going to happen is if you look at a Microsoft application, a Microsoft app will, for example, trying to draw something on the screen here. Sorry. Looks like, well, I won't draw, but a Microsoft application will import directly from those min-win DLLs, and like you're suggesting, basically if someone is importing from API, you can hook that. Now your question is, what if I just import from kernel-base.dll? Can I hook that? Kernel-base itself, though, now actually has imports for all those functions like that. So even kernel-base imports the process APIs by looking them from API-MS-win-whatever. Not all of them, but a big number of DLLs are actually then looked up by kernel-base itself. because you may be importing kernel base because you're a legacy application and you think that kernel base has your heap APIs, but they're not there. So so kernel base has to find where they really are. So it is much more generic than just for applications that use minwin.
Yes, okay, thanks. And the other stuff that it's only a detail. You have said that this hooking method, if you do that, PatchGuard can catch it. But I have not understood how PatchGuard can catch only an user mode hook.
It'll be kernel mode only. So what PatchGuard looks at in Windows 10 is if you do, because the kernel also uses an API set map that's mapped in kernel mode memory for when it loads drivers, for example, if you modify the kernel's map, then PatchGuard is going to crash the machine. So it doesn't protect against user mode, it protects only against kernel mode.
Okay, thank you.
Sure. Anyone else, or is that it? Or okay, thank you very much again. And if you have any questions, see you later.